Okay. (1.6), number 13. Yes. Let me finally no attendance. Benedict says, yeah, if you're wondering why I didn't take attendance, we're actually only required to take attendance for like the first 2 or 3 weeks. After 2 weeks, we have to submit it to the registrar. And once we do that, we're not required. The only reason I take it for like an extra week or so is I just trying to learn people's names more. That's all. All right. Okay. All right. So why don't you tell us what you did with this problem here? Is find the limit. X goes to -3 from above. Again, be very careful with the notation here. This minus sign means you're going to the point -3. The plus sign on the upper right means you're approaching it from the right. So what did you do for this problem?
Hello?
Yeah.
Yeah, so since it's approaching -3 from the right side, in order to find the pattern, I plugged in for the value of x -2.99, which is a number close to -3 approaching from the right side. So for the numerator, when you add -2.99 or 2, you could see it's -0.99, where you could infer that it's heading closer to -1. While the denominator, when you plug in for the value of x, you get positive 0.01.
Right.
That you can infer that you can infer that the number is getting smaller, closer to 0. Because of that, you get like -1.0, which gives you a negative outcome. And since the denominator is getting smaller, the fraction is getting bigger, so the limit would be -infinity.
Yeah. Oh, okay. So that's the correct answer. Let me just say, a slightly better way to do this, or the way that's usually expected, or you'll see in books, is when you see a problem like this. So the first thing I like to do is just plug in the -3 on top and bottom. See, don't forget what's on top is a continuous function, it's polynomial, and what's on the bottom is continuous, right? So the limit should be equal to whatever whatever the y value is there. So just looking at them separately, if you just plug -3 into the top, you get -1 automatically. Now that's already good news, because getting a finite number in the numerator is usually good news, because that means you're probably not going to have major trouble. Remember, major trouble means like 0 over 0, infinity over infinity, something like that. So we don't really need the intermediate step here with the -2.999. The top is simply going to be going to -1 as a limit. Okay, so I would just look at it that way. The bottom, that's where you'd see the problem, because when you plug in -3, you get 0. So as I said, I usually like to start all limit problems by first just plugging in the point and see what I am dealing with, because that makes all the difference in the world. So you obviously were looking ahead and saw what was going to happen. But I would advise everyone at this point, at the very beginning, just plug the -3 in and see what you get. You're going to notice you get -1 on top and 0 on the bottom. Once you have that, you know that the fraction is going to infinity. But like with all these problems, the question is it plus infinity or minus infinity? That's the only issue that's going to remain here. So that issue is going to be determined just by what's happening as you approach, as the denominator, the x in the denominator is approaching the point. So you got to check both sides. Now, in this problem, they're telling you which side we're approaching from. We're approaching from above, which means we're looking at numbers bigger than -3. And what you did here is nice. A good way to get a handle on it is to pick a number that's just a little bit bigger than -3, which would be -2.99 or something like that. and you realize that that's giving you a positive answer. In other words, everything that you plug into the denominator as you approach minus 3 from the right is going to be spitting out a positive number. So we already know the top is going to minus 1. The bottom is going to 0. That means we're going to get an infinity in the answer. But from what we just argued here, we know the top is minus and the bottom is always going to be plus. So it's going to be minus infinity. Okay? So that's how I would approach these problems. Always first just plug in the number in question and see what you're looking at. Okay? For example, if you got a 0 on top and a finite number on the bottom, then you're all done with the problem. The answer is 0. If you have a problem like this and you plug in and you get 0/5, the answer is 0. 0/5 is 0. So, it's always worth just plugging the point in first. But whether the book tells you or not, the problem tells you or not, you always got to remember, if the bottom's going to 0 and the top is something finite, it's going to be infinite, but then the issue is going to become whether or not it's plus or minus infinity. Okay? All righty? Okay, otherwise, fine. All right, let me just show you something here. And as I mentioned before, it's usually a good idea, or it's a good idea, I think, for you guys at this stage to graph the function as sort of a double check on what you're doing, okay? So let me just put this now on the document reader. I finally got a little smart. I decided to set it up before class because it takes forever to get it set up correctly. And so it's all set up. There we go. Okay, so I got to turn this on. Okay, now I already inputted the function that we're dealing with here. Okay, x plus 2 over x plus 3. And here's the graph. And you look at the graph and you can visually see what's happening. This is where minus 3 is, where my pen is pointing. Okay. As I approach minus 3 from the right, you see that I'm heading down to minus infinity. So that's a check on your work that you got the correct answer. Notice if you approach it from the left, you would be heading to plus infinity in this problem. So that would also tell you that if the problem only asks for the limit as x goes to minus 3, you would know the limit doesn't exist because you're getting different answers on either side. So this business of graphing it is usually worth your while. Sometimes, like in this problem, you see it very nicely, and it's just a quick check on your work. Okay? All righty? Okay. Very good. You can't, everyone should be able to see the graph. It's coming up nice on my screen here. Okay, so let me just take this away. Turn this off for a moment. Okay, so thanks. Now, oops, let me put this on the side for a sec. Okay, so let me just check you off. Thank you. Oh, let me point out one other thing. As long as I'm sorry, I took that graph off. Let me just turn this on for one more second. Okay, I just wanted to point out, I think I did already, but I'll just mention again. This is something you've heard and seen before. If the thing is going to infinity, if y is going to infinity as you approach the point, that means you have a vertical asymptote there. But a vertical asymptote is going to occur when the function is going to infinity, plus or minus. The vertical asymptote here is the line x equal minus 3, because the function is not going to touch the line x equal minus 3 because there is no y value when x is minus 3, because the denominator becomes 0. So this line here, vertical line in this case, is a vertical asymptote. Again, a vertical asymptote, the book loosely defines as wherever the function is going to plus or minus infinity. Okay? Okay. So I'm taking this off now. Okay? All right. Very good. Now, the way things worked out, um, that's the only one homework problem that I'd ask that we're going to look at today that you guys did. But I want to go over a homework problem that I said I was leaving for myself. This is number 42A in 1.6. And this is a very difficult problem. And it involves a little trick, which if you've never seen it, you'd have no way of knowing it. So let me write down the problem. It's the limit as x goes to infinity of x times the sine of 1 over x. Okay? Everyone can see that? Okay? All right. Now, Daniel, number 42A, you were supposed to have done this problem yourself or tried it. Okay? Everyone should be caught up on the homework. I mean, let's face it, I don't give an awful lot. There's not too, Okay, okay. So this is 42A, x times sine 1 over x. Okay, so again, I say whenever you approach a limit problem, you always kind of ask what's happening, which usually means plugging in the number. So let's think what's going on here. As x goes to infinity, the x term here, which is going to be multiplying the sine x, the x is clearly going to infinity, right? Let's think about what's happening, though, to the sine 1 over x term as x goes to infinity. So watch this carefully. As x goes to infinity, what does 1 over x go to? That's the limit I said everyone's got to know, basically. As x goes to infinity, what does 1 over x go to? Someone please tell me. 0. Correct. Beautiful. Bingo. Great. Thank you. So as x goes to infinity, this thing, 1 over x, is going to 0. So the question really is, okay, as this thing goes to 0, what is the sign of that headed towards? Because remember, you're taking the sign of whatever in here. Well, the sign of 0 is 0. So as whatever in here goes to 0, what's coming out of the whole term is the sign of 0, which is 0. So if you just start to analyze this limit, what you see is that you're getting infinity times 0. And that's bad news again, because infinity times 0 is like 0 over 0, things like that. It doesn't have any meaning. And it means we're going to have to try to do more work to see if we can figure out what's really happening. Okay? All right. This is the kind of problem you'll deal with very extensively in 152. You'll even learn shortcuts for doing this particular kind of problem. But at this stage of the game, there is a way, which you could use to approach this problem. Because I gave you a little rule of thumb. Remember I said that when it comes to weird trig limits, there is only one right? And that's sine theta over theta. As theta goes to 0, that sine theta over theta goes to 1. So let's see, since that's the only one at this point, let's see if we can get this thing in the form of sine theta over 0. Okay? So yes, you can't manipulate infinity. Infinity is not a number. Right. So the thing to do is, can we get this looking like sine theta over theta? And the answer is yes. If you remember your algebra, I can rewrite that as a fraction with sine 1 over x on top and 1 over x on the bottom. Let me repeat something I mentioned the other day. There's an important algebra rule everyone should review. a fraction divided by a fraction, a over b divided by c over a is the same as a over b times d over c. I'm sorry, a over b divided by c over d is a over b times d over c. Okay. In this case, a is sine 1 over x, b is 1, c is 1, and d is x. So this formula tells you that this is exactly the same as the original thing we started with. Okay? All right. Now let's think through again what's happening. As x goes to infinity, 1 over x here is going to 0. So on the top, we have the sign basically going to 0, the sign of 0. On the bottom, as x goes to infinity, 1 over x is also going to 0. Well, that should kind of ring a bell, because sine theta over theta, as theta goes to 0, what's going on here in this limit? The top sine, I'm sorry, sine theta. The top is going to sine is 0, the bottom is going to 0, and that's equal to 1, but that's exactly what's happening here. The top is going to sine is 0, the bottom is going to 0. So this thing actually is the same problem in disguise. It's sine theta over theta as theta goes to 0 in disguise. If you wanted to do this more formally, if me talking it out like that is a little heavy to follow, let's do it more formally from this point on. Let theta equal 1 over x. So this term here is now going to become the limit sine theta over theta. Okay. The only thing is that the original limit is an x. We now have to get a limit corresponding to that for theta. Well, if we look at this equation, that theta is 1 over x. As x goes to infinity, theta is going to 0. So the equivalent limit for x going to infinity here would be theta going to 0. And we know that equals to 1. So this limit actually goes to 1. In a sense, it's really the same old sine theta over theta in disguise. Okay? Everyone see how I did this? If you've never seen this trick, there's just no way you're going to know to do it. I mean, you know, that's the bottom line on this. But this is a pretty common trick that's used, by the way. Okay, rewrite the fraction algebraically so that it looks like a limit you already know. So that's a very tough problem. Okay. So any questions on what I did over here? That is an odd problem. Okay. All right. So I give myself credit for a problem. So I guess I don't have to do one for a while. I'm going to hold off on some of these other problems. This 48, come back to that. That's more for interest than anything else. All right. So the other homework problem, there's one we have to leave the next time. Person couldn't get it in for me. Okay. All right. Any major outstanding questions? How did I get 0 where, Jessica? At what point are you asking?
So you had limit as limit approaches theta to infinity, and then you went from that to limit approaches theta to 0. How did you get
Oh,
that?
no, okay, no, well, watch this very carefully. The original limit is x going to infinity, not theta, right?
Yeah, that. How did
Okay.
you get from that?
Okay, okay. We're making a substitution let theta equal 1 over x. Okay? Because that converts this fraction to sine theta over theta. You agree with that?
Yeah.
You're with me still?
Yeah.
The
Yeah.
Okay, the problem is we want to take the limit now, but we cannot use the limit for x because this is now a function in theta. So we have to find out what is the corresponding limit for theta when if x is going to infinity. We can't talk about theta going to infinity anymore. We have a new variable. It's not the same variable. X is going to infinity. But the question is, when we make a substitution for a new variable, a new letter, we have to change what the limit is to correspond to the new letter. X goes to infinity corresponds to theta going to 0 by this very equation that tells us how x and theta are related.
Oh.
Okay? You always have to do that if you're going to change your variable, change to a different letter. Okay, we can't use the original limit for x when we now have something in terms of theta, because x and theta are not the same thing.
Okay.
All right?
Yeah, I got that.
Yeah.
Thank you.
Okay, good question. That's important for everyone to get. Okay, that's a general concept that will come up a lot. Will come up later this term. Okay, that when you make substitutions, you have to change your what it equals to correspond to the new variable. All righty? Okay. All right. Let me come back here now. All right. Now, so last time, we introduced the concept here of derivative, and we asked the following question. We said, suppose if we have a straight line and we want to talk about how steep the straight line is, it's very simple. It's the slope. The slope represents the steepness. We discussed that. And we said, all right, but what if you don't have a straight line? What if you have a curve of some sort? There's still clearly a concept of a steepness, because if you look over here, you're going up pretty steep. Okay, here you're pretty flat, and now you're coming down. There certainly is a concept of steepness. Okay, if you walk a trail up the side of a mountain, there's certainly going to be a concept of steepness. Okay, a curve like this instead of a curve like that, clearly there's a difference in steepness. So we want to get a handle numerically on steepness, how steep something is. And the obvious way to do it is by the tangent line, because the tangent line to the curve represents the actual direction you would be looking in if you were walking up the curve. Your eye would be pointed in a certain direction, okay, directly ahead. The extreme case, and the easiest case to see, is a circle. If you're walking around in a circle, so when you walk, say we're walking this way around the circle, if you're over here, your eyes are pointing directly ahead to the left. As you keep walking, when you're down here now, your eyes are pointing directly downward, correct? But if you ask, but all right, what is this direction? What is this line I'm drawing in? It's the tangent line to the circle, okay? It's touching just one point. I could draw it over there just as well. All right. We know also, I gave the other example. I'm saying the same thing in a different way. As I said, if you take a rock and you tie it to a string and you swing it up over your head, and so the rock is going around and around in a circle as you swing it. If you suddenly let go, it's going to fly off on a tangent, because at the second you let go, at the moment you let go, that was the direction it was pointing in. Just like over here, you're pointing to the left, here you're pointing down. okay? So the obvious thing that would represent the slope or the steepness is the tangent line, the slope of the tangent line. And the slope of the tangent line should represent the slope of the curve, the steepness. And that, in fact, is how we define it. That's what we use. Okay, the slope of the tangent line represents the slope of the curve or the steepness of the curve at that point. All right, so the next problem is, how do we get a hold of the number? How do we calculate the slope of that tangent line? And the immediate problem is, unlike a straight line, where you can always pick out 2 points and calculate the change of y divided by the change in x, the rise over the run, well, we don't have that luxury here when we're working with a tangent line, because the tangent line, by definition, is only touching the curve at 1 point. So when we go into this kind of problem, we only have 1 point on the tangent line. So there's no direct way of getting the slope of a tangent line to a curve, because we only know 1 point. You need 2 points to calculate a slope, right? So what we did was we said we'll do a method of successive approximations. Let me just move my notes ahead, by the way, before I go back to that. Okay. So we're going to basically do something, a method of successive approximations. Okay. We'll say we have a curve. This time I'll draw it this way. Doesn't really matter. And I want to get the slope of the tangent line over there. That tangent line is going to look sort of like that. It's only touching the curve at 1 point. That's the definition of a tangent line. So what we said we do is, let's go further up the curve, like to here, and connect the original point, we'll call the original point P, to this new point. That's a straight line. 2 points determine a straight line. This is known as a secant line. A secant line is the line connecting 2 points. And we can indeed calculate the slope of this secant line. Okay, if this is our point A, well, we know what point we picked over there, V. Plug A and B into the function, we get the y value. So we know the x and y value at P. We know the x and y value at the new point. Now just calculate the change in y of the change in x, and that's going to give us the slope of the secant line. All right? That is an approximation to the slope of the tangent line. Of course, it's a very bad approximation. So how do we get a better approximation? Well, we pick a point closer to the point P that we're interested in, and we play the same game. We draw in a new secant line. It's hard for me to draw with this thick marking pen, but you're going to get a new secant line. You're going to get a new point over here. That means we know the x and y coordinates here. We can calculate the change in y of the change in x. So now we have a value for the slope of the new secant line. That's a better approximation to the slope of the tangent. How do we get a better approximation? We pick a point that's even closer to P on the curve, play the same game, draw in the secant line, calculate the slope of the secant, and that's going to be a better approximation. And now if you think about it, if you think about, say, my pen being a secant line, as we pick points closer and closer to P, look what happens to the secant. The secant line starts rotating downward, right? And as we keep picking points closer and closer on the curve and drawing in that secant line, the secant line keeps rotating downward and downward. And if we could keep doing this infinitely many times and come as close as we want to P, we see that in theory, it would seem that if we actually got to P, the secant line would actually become the tangent line. It would lie right on top of it. So if we look at this, the numbers we're getting for the slopes, the slope of the secant here, 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 and we ask, okay, where is that heading to? It's heading to, physically, it's heading to where the secant line is now on top of the tangent line. That number, that limit of those succession of slope values, that should be the slope of the tangent at the point. And that indeed is what we get. And we did a numerical example, the example of y equal x squared at x equals 3 to find the slope of the tangent. And I showed you that by picking points closer and closer, I did this numerically. I started with x equals 4, then we went to 3.5, then 3.1, then 3.01, 3.001, 3.0001. And we looked at the numbers that were coming out for the slope. It looked like it was heading towards 3. Okay, to 6, I'm sorry, as the slope. Okay, let's see if we can show this algebraically. Okay, so we were dealing with y equal x squared, and we want the slope of the tangent at the point x equals 3. Okay, and we're going to do this algebraically. So what we said we did, we know that this point has coordinates 3, 9, because it's y equal x squared. So we say, all right, let's move up a distance and pick a point further up the curve. Now we're going to have to use a number to, or a letter to indicate what distance we went. Let's say we moved up h units. We're going to use the letter h. In other words, the point that we move up to on the curve has an x value of 3 plus h. I have to use a letter because we're going to be changing it. In the numerical example I did, the first h I picked would have been 1 because I said, let's use x equals 4 and calculate the slope of the secant. Okay? So what would be the coordinates of this point? Well, the x value is 3 plus h. The y value is going to be 3 plus h squared. And if we drew in the secant line, what we would get for the slope of the secant line would be the change in the y value, 3 plus h squared minus 9 over the change in the x value. The x value is 3 plus h minus 3. Okay. And let's actually work this out. We have to FOIL out 3 plus h. That's going to be 9 plus 6h plus h squared minus 9 on top. And the bottom is 3 plus h minus 3. That's simply leaving an h. Let me move up the paper. On top, we notice that the plus 9 and the minus 9 cancel out. Okay. 1 second. You can't divide out 3 plus h at this point. I'm being asked by someone, can you divide out 3 plus h? There's no way you can divide out 3 plus h here. I mean, you can't cancel anything on top. That doesn't work. Remember? This 3 plus h does not cancel anything on top by itself. That's not a legitimate law of algebra. So we multiply this out, and now what are we left with? 6 plus h squared over h. That's what this simplifies to. Not 6 plus h. I said it wrong. It's 6h plus h squared, I'm sorry, my mistake, over h. Now we can cancel out this h with this h. This is h squared, so we can cancel one of them with that h. So we get 6 plus h is the result. Okay. So, as I said, if we went from x equals 3 up to x equals 4, h would have equaled 1. Okay. So that would have given us a slope of 7 for the secant line, which is what we did get when we did the problem last class. Okay. The advantage of what I just did here is now we can start getting the slope real quick by just plugging in a new value for h. In other words, if I want to move down the curve from say 4 to 3.5, I just have to change h to 0.5 because 3 to 3.5 would mean h is 0.5. And I plug that in there and I would get that the slope is 6.5, the slope of the secant. And again, if you look back to the work we did the other day, that's what we got. Okay? So the advantage of what I just did here is that no matter which point you want to pick going up the curve and then start coming back down, I have one handy formula to do this for me. But now what we said is we want to bring the point further up the curve closer and closer and closer to x equals 3. Another way of saying that, an equivalent way, is we're going to make h smaller and smaller and smaller. Every time we make this h smaller, we're picking an x value closer to 3, meaning a point closer on the curve. And we said, conceptually, if I let h shrink down to 0, the secant line would now be on top of the tangent line. So the slope of the secant would equal the slope of the tangent. In other words, I'm asking for the limit as h goes to 0 of 6 plus h, which is 6. Okay, you have to digest this a little bit. What I'm doing here is I'm simply redoing the numerical example from the other day, where I successively pick h equal 1, then h equal 0.5. That's the same as saying, let's start from 3, let's go up to 4, and then 3.5, and keep repeating the process. Obviously, for any given problem, you need a more general formula to do it. So I just showed you how we can do that. All right? So that's the answer. Okay. Now, that's well and good, but we need to look at this in a more general sense, because if I have to keep doing something like this for every single curve and every point on the curve, I mean, what if I want slope of this tangent line at 2? I got to go through this whole mess all over again, etc., etc. So we need to really look at this in a more general case and come up with a more general formula that's going to work for any curve and for any point we need on the curve. Okay? So let's set this up. So suppose we have some function, and if we're interested in the slope at the point A, for example, we know the coordinates of A are A comma f of A. Remember, f of A represents the y value. And if we pick some point further up the curve, we move up, say, h units to A plus h. So in other words, we moved, this is h units upward. Then the coordinates of the new point are A plus h comma A plus h, I'm sorry, f of A plus h. I'm doing a very general case now. And remember, we're going to connect and make a secant line and get the slope of the secant line? Well, we need the change in y divided by the change in x. The change of y is going to be f of a plus h minus f of a over the change in x, which is a plus h minus a. And the bottom simplifies, so the top is still f of a plus h minus f of a over h. So this is a general formula for any function. If I want to know the slope of the tangent at the point x equal a, we set this up. These are the secants. And now we need to take the limit of this fraction as h goes to 0. So the slope of the tangent line is the limit of this very fraction as h goes to 0. So now we have a very general result. Everyone kind of with me? This is going to take a while to absorb. It's not an easy concept. All right? All right. This represents the slope of the tangent to the curve or the slope of the curve. Yeah, I know, Daniel. I'm sorry. Unfortunately, it's going to get a little worse before it gets better. All right. So let's actually use this result and go back to the case of y equal x squared. So if y is f of x is equal to x squared, let's actually use this last result. If I want to get the slope of the tangent line to this curve at the point x equal a, we just determined that we need to say take the limit as h approaches 0 of f of a plus rather h approaches 0, f of a plus h minus f of a over h, and let's apply it to the case of x squared. So f of a plus h is going to be a plus h squared. Right, a is some starting point. Okay. Minus f of a. F of a, I'm sorry, is a squared. My error. Over h. Let's multiply out the top. So it's limit h goes 0. When we square this out, we're going to get an a squared plus 2ah plus h squared. We still have a minus a squared on top. All this is over h. And the top now simplifies. A squared and minus a squared cancel. So we're left with 2ah plus h squared over h. And this h cancels the 1h and 2ah, 2a, and it cancels one of the squares. And now as I take the limit as h goes to 0, this leaves me with 2a. Right. So let me repeat what I've just found, because it's easy to lose that from all the work in between. I've just found a general formula that for the graph y equal x squared, the function x squared, if I want to know what the slope of the tangent line is to that curve at the point x equal a, I now have the general formula. It's 2a. for any x, any value you want. So if I want to know what is the slope of the tangent line to the curve x squared at the point x equal 2, I don't got to do a lot of calculations now once I knew this. It's simply 2 times 2 is 4. Okay? What if I want to know the slope of the tangent at the point x equal minus 3? Drew this lousy. It's 2 times minus 3, which is minus 6. That makes sense because if you look at the graph, if you look at a decently drawn graph, which you don't get from me, I'm afraid, the slope of the tangent is negative. It's pointing downward. So we now have a very general formula. Okay? Yeah, unfortunately, right. Yes, I'll come to that. You're basically going to have to know how to do this. All right. Okay. Now, but the even more general form, no, the answer is 2a. It's 2ah before you take the limit as h goes to 0. Taking the limit of 2a plus h as h goes to 0. As h goes to 0, this whole thing goes to 2a. That's the answer. Remember, the slope is found as a limit. Okay? The even more general way of doing this problem is to just say, okay, I have f of x is x squared. Okay? Take a point x. Don't even bother bringing in the letter a. Go up a distance h. So now you're the point x plus h. The coordinates of this point are x comma f of x. The coordinates of this point are f of x, x plus h comma f of x plus h. So the slope of the tangent at the point x is going to be limit h goes to 0, f of x plus h minus f of x over h. This term f of x plus h, if you look back in your homeworks, you'll see that you had this homework in an earlier section, something about evaluating f of x plus h. There's a reason. I'm being asked, should this be squared? No, because f of x plus h means I haven't yet plugged x plus h into the function. The symbol f of x plus h means I got to plug it into, right? So now I'm going to do that. What is f of x plus h? Well, if this is f of x equals x squared, remember, whatever's inside the parenthesis replaces the x's on the other side of the equation. That's why we stressed that a couple of sections back. So that becomes x plus h squared. F of x is simply x squared over h. Okay. Now multiply out the top, and you're going to get an x squared plus 2xh plus h squared minus x squared over h. And if we algebraically simplify the numerator, the x squares cancel. And once again, we're left with 2xh plus h squared over h. The h divides out that h, and one of the squared h is there. So this leaves 2x plus h. And we're left with 2x. You're talking from here. Am I being, you're asking, I'm asking a question. Is it from here to here? Is that what you're asking me?
Yeah.
Well, what does f of x plus h mean? That's why we had that homework problem. F of x plus h means you take the formula for f of x, whatever's in this parenthesis replaces the x's on the right side of the equation, correct? That's how I get this. And what it represents here is the y value at the point x plus h. Is that clear?
Not really.
This is very, very basic. This is stuff we did in the homework in section 1.1 and 1.2. Okay, I mean, you got to go back and review it. That's one of the things we review this. I mean, if f of x is equal to x squared, what does f of 2 equal?
4.
Because it's 2 squared, right? What does f of a equal?
A squared.
A squared. What is f of x plus h equal?
X plus h squared.
Yeah, right?
Mm-hmm.
Now
Oh,
you
I
see where,
Yeah,
now I
yeah,
got it?
yeah.
Okay, this is crucial. This is crucial. That's why I reviewed it. Please go back and review it because we specifically had this in a homework, an f of x plus h problem. The reason is the book knows this is coming up, and that's why they throw it in there. Okay? All right. So let me just tell you though, this result here. So we have the most general result now. If I need the slope of the curve x squared at any point x, I plug it into 2x and I got the answer. So the slope of this curve x squared at the point x equal 10, that slope is 20. I just plug it in. So I don't have to keep recalculating the same thing over and over and over and over. All right. We are going to very shortly see that there are shortcut formulas to these problems. In particular, there's going to be a shortcut formula for calculating this for any power of n, x to the n. We're going to learn a shortcut formula. But before we learn the shortcut formula, everyone has to learn how to do this. Unfortunately, they always ask this. They ask this on the departmental finals all the time to be able to do this calculation. And there are a couple of homework problems where I ask you to do this. And you need to also read the examples in the book where he does it. Be sure you follow each step. But once you do this, once you know this, and then we learn the general formula, you will almost never, at least in a first year calculus course, go back to doing it this long way. This is known as doing it from the definition. Okay? All right. We say that the result of doing this, the thing that comes out of here, 2x, that's known as the derivative of the function x squared. That's the word. It's the derivative of the function. And we'll say a lot about that momentarily. Okay? So the derivative of x squared is 2x. Okay? All right. Just to make things even more confusing, there is a slightly alternate way. Instead of using the limit as x goes to 0 of f of x plus h minus f of x over h, there is a slight alternative way which is completely equivalent but comes up every so often as useful. So if we call this point A, and this is where it gets confusing, and we call this point further up the curve X, yeah, just to make it more confusing. Okay, I'm setting up the same concept in a slightly different way now. which is confusing compared to the last one. So the coordinates at this point are going to be a comma f of a. The coordinates of this point up here now are going to be x comma f of x. In other words, we're not using an h here. We're just saying I go further up from a to the point, any point x, some point x. Now, if we draw in the secant line, we need the change in y. Well, the change in y is f of x minus f of a, f of x minus f of a, divided by the change in x, which is x minus a. Okay. And now we want to take points closer and closer to a. So if you look at the graph, the picture, taking points closer and closer to a means we're letting this x value approach a. This x is going to get closer and closer to a. So I mean, if this a is 3 and the x is 4, we're going to move x down to say 3.5, then 3.1, then 3.01. So when you set it up this way, the limit we need is x is approaching the point A. So this is an alternative way of saying the same thing. If you don't want to bring in the letter H, you can set it up in theory this way. These two approaches are absolutely identical. Truthfully, we don't use this too often. Everyone remembers this first one, but you have to recognize this one, and we do need it to prove a very important theorem we're coming up to. Now, A is picked as the fixed point. We want to find the slope at the point A. I'm being asked about, can't we say the limit x goes to A? No, 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 no. The whole point is to get the slope of the curve at the point A, right? Okay, so we're going up to some other point x, and that has to vary. There's no different in the concept here. It's just the way we're setting it up. Unfortunately, we need this. We need this to prove a very important theorem we're going to prove. Okay? All right, so let me just give you a piece of notation. We're going to come back in a second to notation. One of the common symbols that's used to denote this thing here, I said it represents the derivative of the function at the point x, is this symbol, read f prime at x, but there will be other symbols. We're coming back to the symbols, don't worry about it. All right, we now have to go to another question, which at first may seem fairly unrelated and may even question why we're doing this or whatever, but it's actually the original question from the real world that inspired all this. Okay. All right, so let's start off with a very simple problem. So suppose I get in my car and I drive for 2 hours at 10 miles an hour. No, scratch that. Let me restart that. It'll be easy to do it this way. Suppose I get in my car and I drive for 2 hours and I discover that I am now 30 miles. I've gone 30 miles. Okay. So I get in my car, I drive 2 hours, and I find that I've traveled 30 miles at the end of the 2 hours. So what is my speed? My velocity? If I cover 30 miles in 2 hours, what's... Come on, guys, this is a 6th grade question. You do this calculation all the time. If I drive for 2 miles and I discover I covered 30 miles, it's 15, but so my speed here is 30 miles over 2 hours, which simplifies to 15 miles per hour, right? This is not a trick question. Unlike many of the ones I asked, this is not a trick question. It's straightforward. You know how to do this stuff when you're a kid, okay? You do it all the time. Whenever you take a trip, you often do this. Okay. Okay. And yeah, so this is the speed. Okay. Another word used is velocity, although velocity actually has a very slightly technical different meaning in physics, but we'll just use it as the same word for now. Okay. But this number is really just an average because it's misleading, because you think I'm going 15 miles an hour for 2 hours, but then I tell you, but that's not what I did. The car was parked and I got into the car. The velocity initially was 0. Then I accelerated up, all right, and I was driving on a city street at 5 miles an hour and I came to a red light. So I had to stop there for a couple of minutes. And then the light changed and I got onto the highway and I accelerated up to 50 miles an hour for a while. And then when I got off the highway, I had to go get off the exit ramp. So I went down to 20 miles an hour. And then I came to another red light and I stopped. And then I went up a side street where I only went 5 miles an hour. And then I parked. All right. So this number is actually very misleading. This is an average. And like all averages, like when we take the averages of exams, even things like that, the class average, it only gives you a general picture on average of what happened. On average, you could say I went 15 miles an hour. The reality is, though, I didn't go 15 miles an hour. There were times when I had 0 miles an hour. There were times when I was going much higher. It averaged out to 15. Okay? So this is only what we would call an average velocity or an average speed. And like I said, like everything else, you don't know what to necessarily make of it. It just gives you an average. Okay. But the real interesting problem in physics is, well, wait a minute. What exactly was your velocity? Say you drove for 2 hours. What was your velocity exactly 1 hour into the drive? Well, I don't know. Maybe I was on the highway went 1 hour into these 2 hours and I was at 50. Yeah, but maybe at an hour and a half, I was at a red light and it was 0. The real problem that physics needs to answer is, well, what is the velocity at any instant, at any time? This really doesn't give us too much information. You know, all kinds of trips could be described this way. I mean, you could have driven 15 miles an hour straight for 2 hours, okay? Or, you know, you could have stayed still and then in 5 minutes accelerated up and driven the entire 30 miles in a couple of minutes. That averaged out to 15 miles an hour. So what we really need to know is, what is the velocity at any moment? And we call this, this is the average velocity. What we want to know is the instantaneous velocity. Instantaneous velocity. That's the real question. And that was the question that Isaac Newton was trying to answer. Okay? I want to know, what is this thing doing at any specific time? At 1 second after it leaves, at 2 seconds, or in this case, at half an hour, at 45 minutes, at 1 hour. All right. So let's come back, first of all. So suppose we take this trip and we actually do drive at exactly 15 miles an hour. And if I graph the distance, and we usually use the symbol S, okay, for distance, and we make a graph of the distance versus the time. suppose I really did go the whole thing at 15 miles an hour. Suppose I was already driving at 15 miles an hour. I drove past you and you turned on a stopwatch, and then I just kept going for 2 hours. So in that case, I was always going 15 miles an hour. If I wanted to graph the distance traveled against the time, well, there's 1 hour, 2 hours. At the end of 1 hour, I would have gone 15 miles. And if I keep going, at the end of the second hour, I would have been at 30 miles. Okay. Think of what the average velocity here represents. Why? It represents the slope of that line, doesn't it? Because I started at time 0 at having gone 0 miles, and I ended up at time 2 hours having gone 30 miles. And if I take the average, that's taking the same thing as taking the slope of this line. It's the change of the dependent variable s. We use s instead of y, 30 minus 0, over the dependent variable, which is time t, over 2 minus 0, that's 15. In other words, the slope of this line is the velocity. If you maintain a constant velocity, if you don't keep changing your speed, and you graph the distance covered versus the time covered past the time that's passed, it is the slope of this curve that's your velocity. Yeah. And that's the key thing. In general, if you graph distance versus time, the velocity is the slope of the curve. Well, now suppose I take the kind of trip that I described where I started at 0 and then I went 5 miles an hour for a little while. So I covered this much distance. I got on the highway and I accelerated up. So now I'm covering a lot more distance in a short period of time. And then I slowed down when I got off the highway. And then I came to a stop sign and I stopped. So I didn't cover any distance for a moment. And then I went something like this. So if you keep changing your velocity during the trip, you're not going to get a straight line. You're going to get a curve of some sort. And if I asked you, what is the velocity at this exact time right here? Well, it's still going to be the slope of the curve, except now the curve is not a straight line. It's curve. So we need the slope of this curve. So the instantaneous velocity is the slope of the curve at that time, at time t, equal to the slope of the curve at time t. So if I want to know the instantaneous velocity, I need to be able to get the slope of the curve when I graph distance against time, and that's going to give me the instantaneous velocity. This was the actual problem that Newton started with. How do we get an instantaneous velocity? Okay. And the answer is, it boils down to getting the slope of the tangent to a curve. And we've heard that one before. We've solved that problem already. We got to do what we just did, getting these slopes of tangent lines. And it's going to be the same exact process. Okay? This is what led Newton to work this all out, this kind of problem here from physics. Okay? as I said, when I first started this, I could have presented this velocity problem first, but it's a lot less intuitive. It's a lot harder to follow. The geometric approach, thinking in terms of a tangent line, is a heck of a lot easier. So let me just give you now a little example. Okay, a real life example. Let me move this away. Suppose I go to the roof and I drop a ball from the roof and at time 0, and I turn on my stopwatch at time 0, and I let the ball drop down. Okay. It is a well-known formula in physics that the distance the ball travels to time, the distance s that the ball travels to get to time t, it's given in physics as 1/2 gt squared, but we'll use feet and seconds. G is just a number. If you haven't seen this, it doesn't matter. It turns out that this boils down to 16 times t squared. So if I drop a ball from the roof and I want to know how far has it fallen by the end of 1 second or 2 seconds or 3 seconds, this is the formula. If I now add, so in other words, by 1 second, this is in feet per second. This is in feet. So at 1 second, I will discover the ball had fallen 16 feet down already. Okay. At 2 seconds, it's 16 times 4, that's 64. I'll see that the ball is now fallen down 64 feet below where I dropped it. So if I now ask, well, what is the speed of the ball at 1 second and 2 seconds? That speed obviously is changing. Okay. Well, the answer is if I graph s versus t, the distance versus the time, and I plot this out. This, by the way, graphs out here also as a parabola, just like x squared is a parabola, t squared is a parabola. If you multiply by 16, it turns out it's still a parabola, only it's steeper. Okay. And if I want to know now, okay, what is the velocity of this thing at any time? Velocity is a function of time. Well, it's the slope of the tangent. We already know how to get the slope of the tangent to x squared. That's the same as t squared. It's 2t. Just accept my word for it at this point that multiplying by 16 just multiplies that 16 times 2t. This is something we'll come to. So this quickly gives us a formula for what is the velocity of this ball at any time t. So in other words, 1 second after I dropped it, it's going at 32 feet per second. 2 seconds after I dropped it, it's going at 64 feet per second. It's accelerating. This is the real world value of this, but this is only one teeny example. Okay. If you read it through the book will expand more on this. I don't want to spend too much time on this. Okay, it's hard. You got your work cut off you already, just understanding what we've done so far. The geometric presentation, as I said, is a lot easier to get your head around. It's more intuitive. Okay, but this is one of the big uses of it. Okay. All right. So far, this process of getting the slope to the tangent, I said we call this the derivative of the function. We now have two interpretations. Number one, it gives us the slope of the tangent line to the curve. A second interpretation is it gives us the instantaneous velocity, the velocity at any time. If our function is distance relative to time, s of t. There's one last interpretation, which I actually already alluded to. We can sort of see it from here. What is a velocity if you think about it? Well, a velocity is a rate, right? Like 20 miles an hour, that's a rate. It tells you how fast one variable is changing as the other variable, right? For every increase of 1 hour, I increase 20 miles in distance. Okay? Remember, I said a slope is also represents a rate in general. I said if I tell you that the slope of a line is 6, that means for every, say, 1 meter I walk in this direction, I will discover, this is drawn ridiculously off scale, I will discover that I have gone up 6 meters in that direction. Okay, if I walk another meter up until 2, I will now discover that I'm 12 meters up. If I ask you how fast am I going upward, answer 6 meters per second or whatever it is. Okay. This is all sounding vague and hazy at this point. I know it's getting more and more hazy because there's a lot here and it's not easy and you're just seeing it. But the third interpretation of this derivative thing is it represents the rate of change of the dependent variable as the independent variable changes. Okay, so let me just write this down. This thing that we're now calling the derivative, given y equal f of x, has 3 interpretations. They're all equivalent, really. One, it's the slope of the tangent line to the curve if we graph y equal f of x. That's interpretation number 1. Interpretation number 2 is it's the instantaneous velocity okay, if y is distance and x is time. In that specific situation, it's the instantaneous velocity. The third thing, and again, these are really saying the same thing in different ways. It's the rate of change. Now I'm going to throw another curveball at you. It's the rate of change of y with respect to x. Now, before everyone breaks down in tears here, let me give you a moment to write this and explain. I know this is a lot. It's not easy. This is hard. The good news is after we get through this little piece, it's temporarily going to get easier. We're just going to learn a bunch of easy formulas that we use, how to use this. This is the hard part. Okay, so there are 3 physical meanings of derivative. It's the slope of the tangent line to the curve. It's the instantaneous velocity if your curve is a curve of distance versus time. And it also is the rate of change of y with respect to x. That's the terminology we use, which means how much does y change as x changes? That's this third illustration here. For every 1 unit change in x, y changes by 6. You must know these 3 things cold, okay? We're always amazed when we see students come to the end of the term, or students come into 152, and you say, what's the interpretation of derivative? And no one knows. You've got to know these interpretations. That's what it means physically. Number 1, it's the slope of the tangent to the curve. Number 2, it's the instantaneous velocity when you graph distance against time. And number 3, it's the rate of change of y with respect to x. All right. Everyone in a state of shock now? Okay. All right. Okay. All right. So now moving on with, all right. Can I take this away? Okay. Now, we have to also realize something else here. And we also need to start calculating some more examples of derivatives. We said that if y equal f of x equal x squared, this thing we call a derivative, I said that the derivative which one symbol for that is f prime x is 2x. An important observation here is that the derivative is also a function. It's a brand new function that we manufactured from x squared. And that's always true. The derivative will be a new function. All right. And the book calls this next section the derivative as a function, viewed as a function. Okay. All right. Let's look at an example. Oh, before I say that, let me just point out a serious error we see all the time. Do not please write x squared equal 2x. That is wrong. X squared does not equal 2x. The derivative of x squared equals 2x. And yes, it's a big difference, and yes, it matters. Okay. I showed you how we calculated out from the original definition this general formula. Let's do that for another function. And it's also a good chance to review limit work. This problem is one requiring a little bit of limit review. Let's look at y equal f of x equal the square root of x. Let's, by the way, point out, what is the domain of this function? Someone tell me, what is the domain of this function, square root of x? Someone tell me. Is it all that? All, that's very good. Yasser's right. Yeah, it's all non-negative values. In other words, the domain is x squared equal to 0, all non-negative values, because you can't take square root of a negative number. That's correct. Keep that in mind for later. All right. I want to get, if I graph this thing, I want to see what is the slope of the tangent line at any point x that I like. By the way, I'll just quickly show you roughly what this graph looks like. It looks sort of like that. Okay. And I want to know if I'm at some point x, whether it's x equal 2 or 4 or 16 or 20, whatever it is, I want to know what's the slope of the tangent. So we'll use this new symbol already. We know it's given by the limit as h goes to 0 f of x plus h minus f of x over h. That's something you got to be able to like say in your sleep. Okay. Now let's start plugging in what these things equal. So if f of x is root x, what is f of x plus h? It's square root of x plus h, right? Minus f of x is root x. Okay. Okay. All right. So we got to evaluate this limit. Now, as I said, h is going to 0, so I always like to first plug h in. If we plug h in as 0 here, the top is going to be root x minus root x. That would be going to 0. The bottom h would be going to 0. We got 0 over 0. That means trouble. It means we got to do some more work to see what exactly is happening here. So we learned already that there's a standard trick for handling this kind of a limit when it's not cooperating nicely with us. Someone tell me, what is the standard trick for doing this kind of a limit? Grr. No. Someone's saying to multiply by the conjugate. Very nice. Thank you, Richard. Yeah, this is, remember I said one of the things you do with radicals, multiply by the conjugate. We're going to multiply top and bottom by root x plus h plus root x over root x plus h plus root x. That's exactly what we're going to do. Multiplying top and bottom by the conjugate. You obviously multiply top and bottom by the same thing because that equals 1, so it doesn't change the value of anything. Okay. So remember, these things are really think of better in parenthesis. So we got to FOIL this out. So root x plus h times root x plus h leaves an x plus h term. Root x plus h times root x is going to be plus root x plus h times root x minus root x times root x plus h gives us minus root x plus h times root x. And root x times root x is x, but it's got a minus sign, right? So it's minus x. And here's an important hint again. I mentioned this before. Don't multiply out the bottom at this stage of the game. Just leave it for now. Okay? Now let's simplify the top. Okay? These two terms cancel. So I'm going to get x plus h, and then there's a minus x in the end, over h times root x plus h plus root x. X minus x, that disappears. So on top, I'm only left with an h. And on the bottom, I'm left with the same term, h times root x plus h plus root x. And the h is canceled. This is why I said I'll multiply out the bottom at first. So now we have the limit as h goes to 0, 1 over root x plus h plus root x. So now we need the limit as h approaches 0 here. So as h approaches 0, the root of x plus h simply goes to root x. So this is root x plus another root x gives me 2 root x on the bottom. The top is simply 1. And that's our answer. The derivative of the square root of x function is 1 over 2 times the square root of x. Write it that way. So, for example, at the point x equal 9 on the curve, what's the slope of the tangent line? Well, square root of 9 is 3, so it'd be 1 over 2 times 3. It would be 1/6 would be the slope of the curve. And up here on the picture, you know, it would look something like that, the tangent line. Okay? Okay. Let me repeat. When we work out these problems directly from this is, we call this getting the derivative from the definition. This thing here now becomes what we call the definition of the derivative. This limit, that's the definition. Okay? Again, as I said, you need to learn this, but we're going to very shortly learn a formula for getting the derivative of x to the n. By the way, notice this is an x to the n problem. Square root of x is the same as x to the 1/2. And as I said, I think in the first day of class, you've got to know exponents cold here because all these rules are going to be given in terms of exponents. Let me make one other last interesting observation here. We said the domain of the original function is x greater to 0. I mean, the x values that are allowable are x greater to 0. The derivative is a brand new function. Here it is, 1 over 2 root x. What's the domain of this function, the derivative itself? Is it still x greater to 0? Richard? No, what is it? What's the new, the domain is a little different now. Why? It can't, excellent, yeah, very nice, very nice. Yeah, the new domain here is simply x greater than 0. For the original function, I can plug in 0 into the square root, correct? But in this derivative, I cannot plug in x equals 0 anymore. So notice that the derivative is a new function, but it has slightly different domain. And there's a good reason why that happens. We can get a nice physical interpretation in this case. Let's look at this graph for a second. If I went to try to draw a tangent line at x equals 0, if I drew this in really well, we would see that the curve becomes vertical. The tangent line becomes vertical. Okay? And remember, a vertical line has no slope defined. And that's what's being reflected in the fact that in the derivative, we can't plug in 0. There's always going to be a correlation. There is no derivative at 0. Okay? All right. So this is a good review of some limits. Okay. So now let's summarize now. So if y is a function of x, we say that the derivative of y, and I like to always say with respect to x, because if you use a different letter, it's going to be with respect to something different, is defined as the limit as x goes to 0, f of x plus h minus f of x over h. Okay. And last few moments, we said that f prime of x, and this is red prime, f prime. So we said that that's one symbol for the derivative. In fact, there are tons of symbols, okay? And let me just show you some of the other symbols. And we use all of them so frequently that you're going to get used to them. You don't have to necessarily memorize them. Another symbol, all these symbols mean the same thing, is to write dy dx. This is not a fraction. Warning, that is not a fraction. This is a whole symbol that cannot be picked apart. It's a symbol. Another way we could write it is df dx, since y is f of x. We sometimes write d dx and put the f out there. And sometimes we would actually put the function right after this d on top. Like if I wanted to indicate derivative of x squared, sometimes we actually just write the x squared right in there. And one other very common symbol is just to write f prime. So 1, 2, 3, 4, 5, 6. So there are 6 different symbols here. All right. And let me caution you that these things here are not fractions. They're symbols. They cannot be pulled apart. Warning. Okay. Let me just give one quick quick historical footnote. This f prime notation essentially comes from Newton, not directly. The other person who invented calculus, literally at the same time Newton did, was a guy named Leibniz in Germany or Austria. Newton, of course, was living in England. Turns out Leibniz invented it at pretty much the same time, and they published separately. Well, Newton didn't publish till later. That was one of that led to a big controversy of who gets the credit, but it was essentially done at the same time. This D symbol with the D's in it, that's all due to Leibniz. And it actually turns out to be probably the most important set of symbols that are used. Our book loves to use F prime, and I like F prime also for certain things. However, the D symbol is going to be profoundly useful, okay? It's really useful for memorizing certain equations that we're going to learn and stuff like that. So you have to be conversant with all of them, okay? All right, so Um, I think that's more than enough for today. I'm sure everyone will agree. I'm sure everyone is ready to cry. Um, okay, let me just see about assigning some more problems. Okay, yeah, I can assign a couple of problems. Okay, so in fact, let me just, well, I warn you that this is an accelerated class. I remember how much time I spent on saying that the first day. Believe me, I knew what I was talking about when I said that. Okay. Uh, okay. All right. So in 1.6, we have problem 21. That's a limit problem. Okay. Um, someone like to volunteer for to have it ready for Thursday? Preferably someone hasn't done one yet, preferably. Is there anyone who's willing, who hasn't done one yet, who's willing? Anyone? Okay, so I guess it's sold to you, Yasser. 1.6, number 21. Let me just give you a suggestion about doing that problem. I suggest you put everything into exponential notation. It just makes it a little less messy to deal with. Okay, that's a suggestion. We also, let me just see, in 2.1 now, we have a couple of problems we can assign. Okay. 2.1, number 25. That's getting a derivative from a definition. Okay, so Christine, no. Which Patel just? I have two Patels in this class. Which one was it? Rishika. I'm sorry. Okay, Rishika. 2.1, number 25. That's actually getting a derivative from the definition. It looks just like the one I did in class. Okay, and let me just see what else we have. Okay, we can also do 2.2, number 19. That's again getting it from the definition. It's a much easier one though. Anyone want to grab that? 2.219, it's an easy one. I don't lie to you. When I tell you it's easy, it's easy. Okay, let me just see who was the first. Preferably, let me just see who hasn't done one. Well, who was the first person? Um, I'm sorry, I'm looking at the wrong list. I'm trying to look at the. Okay, you already did one. Who hasn't? I'm just trying to see if any of the okay, all the volunteers have done one. So I guess we'll take the first one then. Benedem. Okay, so you own it, Benedem. Okay, that's 2.2, number 19. Let me just take 2.2, number 19. And I can also give you 2.2, number 27. I'll leave that for next time. I'll leave it for next time. That's enough. Okie doke. All righty. Okay. Let me just see one thing here. One, I think you and I need to talk about something. One, okay. Either email me or whatever. Okay. All righty. Okay. Oh, and Yogan, we'll do your problem on Thursday. Okay, I explained that to you, right? Okay, so I guess that's about it. I'll let you have 5 minutes earlier to recover from that. No, there's not. No, there's not going to be a quiz this Thursday. I have to announce it, give you advance notice, and I didn't say anything about it specifically. Okay, all righty. Okay, guys. So in that case, we're having them eventually. Okay, so in that case, I'll see you on Thursday. I don't have specific date set up yet. I'm conflicted about all that. Okay. All right, guys. So we'll see you on Thursday. All righty. Okay. And Juan, please get in touch with me. All right. Take care.